Yes, Atif, Aisha, Uzaifa, just check. The screen is not sharing. Okay, it's sharing. Fine.
Can see.
All right. Okay, see, so we had left on this question. Before that, let's just discuss. So yes, Atif, tell me, what was Coulomb's law? Till the time Atif is replying, others also write me in the chat box, what was Coulomb's law? Good evening, Shravya.
Should I say the formula or the like the what is
The
it proportional?
electric force is proportional to all the quantities. Just tell me that.
Okay, electric force is proportional to the product of. Okay, if two charges are separated by distance r, then the electric force is proportional to the product of the magnitude of these charges, and it is inversely proportional to the square of the distance between them.
Perfect. It is inversely proportional to the square of product distance between them. Yes, Shravya, you're also right. And yes, Aisha, that is the formula. So yes, Aisha, you have written K. What is meant by that K? Any formula for K or any value for that K constant that we have? Yes, Aisha. 9 into 10 to the power 9. Or yes, Shravya, you're also right. 1 by 4 pi epsilon naught. So the value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So fine. All right. So we had left on this question. So did anybody get the answer? Just write me your answers if you have solved this. Let's discuss it together then. No answers till now. All right, see, it says that two charges Q1 and Q2 are placed at a separation r, they repels each other. It means if we have a charge Q1, we have a charge Q2, both of these are separated by r. Then I say both of these repel each other with a force F. It means these are like charges and they must be repelling each other. So let's say F is the force with which both of these charges repel each other. Now see, if F is the force, like clearly how Atif said, this will be equal to K, the constant that is used. Product of these two charges, it will be Q1, Q2 divided by R square. So is this clear till here? If we have two charges which are separated by a distance r, we'll write the formula of electric force as K Q1 Q2 by R square. This is the first equation that we have. Now see, in the second part of the question, it says we have to calculate force if magnitude of both the charges is doubled and the separation is halved. It means now this will be 2Q1, this will be Q2 Q2, since the magnitude of both the charges is doubling. And the radius will get half, means that if it was r initially, now it will be r by 2. So this will be the new force. So let's say if the distance has changed, if the charges has changed, then obviously it will affect the electric force. So electric force will be equal to now, not F, let's say F prime, let's say F dash is the new force that we have. Now K is the constant, that will remain the same, 9 into 10 to the power 9. Regarding it's r square by 4. Yes, when r by 2 will get squared, then it will be r square by 4. So see, this will be K. Then we have Q1 instead of Q1, we have 2Q1 right now. So this will be 2Q1 instead of Q2 that we were having initially. Now the magnitude has doubled. So we'll be writing it as 2Q2 divided by. Now see r square. Now we cannot directly write r square. Instead of r, we have r by 2. So it will be r by 2 now whole square of this. See, what does Coulomb's law say? It says that the electric force is inversely proportional to the separation between the two charges. So if these are the two charges, Q1, Q2, these are the two charges. So electric force, whatever electric force will be there between these two charges, it will be inversely proportional to the distance between these two. It means it will be inversely proportional to square of the distance, that is r by 2. So that's why we'll write r by 2 whole square. Now if we simplify this, this will be k, 2 multiplied by 2 will be 4, q1 q2, 1 whole square, r by 2 whole square, r will be r square, and instead of 2 we'll be having 2 square. See, r by 2 whole square will be what? R square divided by 4. So this 4 will go up. So this will become 16k q1 q2 divided by r square. Now if you can easily relate with the first force that we have, what is k q1 q2 by r square? F. It is F. So it means F prime, or the new force, this is 16 times the original force. So F prime will be equal to 16F. Is this clear now? Or you can simply take the ratio of both of these also. So K Q1 Q2 by R square will get cancelled with this. K16 will be left only. So just note down the formula. I think you all have written the question. Just write down this formula. All of you have written this now? The solution was shorter.
Yes, teacher.
All right. Okay, fine. See, let's discuss one more topic over here. If you remember this, K was written as 1 by 4 pi epsilon naught. So I had told you that this epsilon naught will be discussed. Now let's see what is meant by this epsilon naught. See, epsilon naught is basically known as dielectric constant, or the relative permittivity. Relative permittivity. So this dielectric or relative permittivity actually determines how the force will be affected in a medium. See, all right, okay, it's iftar time right now, so let's take just 10 to 15 minutes break. I'll come back, then we'll continue. All right, so just stay connected. I'll come back.
Okay.
Yes, hello. Is this audible?
Yes, ma'am.
All right. So fine. So we were discussing dielectric constant or relative permittivity. Okay, see what is meant by permittivity. See, when two charges are placed in any medium other than air, the force between them is greatly affected. So permittivity is the property of the medium which determines the electric force between the two charges situated in that medium. For example, if I tell you F is equal to K Q1 Q2 divided by R square. Now see, if I'll open and write this, this will be 1 by 4 pi epsilon naught Q1 Q2 divided by R square. Now see, this epsilon naught is having certain value for which the value of K, this is 9 into 10 to the power 9. If we change the value of epsilon naught, if you change the denominator, if you increase the denominator, then the whole value will get decreased. And if you increase the denominator, then whole value will decrease. So vice versa, it will happen. So see, F is equal to K Q1 Q2 by R square. So F is also having certain value for the value of K as 9 into 10 to the power 7. Now see, if you somehow change the medium, then this epsilon naught gets affected. This epsilon is a symbol for the relative permittivity of the medium. So now what will happen? Once you will change epsilon, now epsilon's value, this will be something else for different medium. Like for air, what was the value for air? If any of you remembers, we had discussed it. Yes, Arthur.
And 10 raised to 9.
That was for K. See, that is 1 by 4 pi epsilon naught. Epsilon's not specific value.
8.85 to 10
Yeah.
to the power minus 12.
8.85 into 10 to the power minus 12. So see, when you put 1 by 4 into 3.14 into 8.85 into 10 to the power minus 12, then you get 9 into 10 to the power 9. That is what we write for K. So see, for free space, we have this value. This is for free space. Basically, by free space, I mean air. If the medium is air. So if your medium is air, so if the medium is air, then it will be epsilon naught. So for F air, this is force in air. You can use this value Q1, Q2 by 4 pi epsilon naught R square. Now, if there's a medium, if I say this is not free space, this is some medium. So let's say Q1, Q2, both of these charges are present and these are separated by separation R. Now see, force for a particular medium. This will be 1 by 4 pi epsilon, not epsilon naught. It will be epsilon and it will be having its respective value for different mediums. Then it will be Q1, Q2 divided by R square. So here epsilon is not the relative permittivity. Here it becomes the absolute permittivity of the medium. Here it is absolute permittivity of the medium. This is epsilon. Now see, epsilon naught, these can be related. So if you wish to relate the relative permeability, see, if you divide absolute permittivity, that is epsilon, by relative permittivity, epsilon naught, then you get this value as, you can write this as epsilon R also, that denotes the relative permeability of both the media. In other medium, we consider epsilon instead. Epsilon will be different for different media. Like if you say for air, it is 8.85 into 10 to the power minus 12. So that's what we represent through epsilon naught. Just to represent vacuum, wherever you have to represent vacuum, usually we write this symbol 0 in the subscript. That becomes epsilon naught. If you have different medium, let's say you have a different medium, supposedly water. So you can write it as epsilon W. So that will be having a certain value. Then you have different medium, let's say glass. So you can write it as epsilon g, that will be having its certain value which will represent the value of the permittivity of the medium in glass. So just specifically for air that we have, but for different media you can have different values. All right, now see, if you have two medium, so epsilon means absolute permittivity of the medium. Epsilon naught is the permittivity of the medium in free space. Their ratio gives you absolute, now it gives you relative permittivity of the medium. So see, the ratio of absolute permittivity of the medium to the permittivity of free space gives you the relative permittivity of the medium. One more thing, we have studied this K, this constant, whose value in air was 9 into 10 to the power 9, this K. So you can relate it to epsilon and epsilon naught as well. See, epsilon divided by epsilon naught, this is also K, this is also equal to K. So epsilon is equal to, from here you can say epsilon is equal to relative permittivity of the medium multiplied by permittivity of free space. From this equation you can just cross multiply both of these, you can get the value of epsilon, or from this equation also you can get the value of epsilon. So this will be K multiplied by epsilon naught. So these are the two values of permittivity, relative permittivity that you can have. Now see, if you have the value of epsilon with you and you wish to relate it to epsilon naught, like in the previous part, here let's say F in medium we want to calculate. So force in medium is given by 1 by 4 pi epsilon q1 q2 by r square. So F is equal to 1 by 4 pi epsilon for free space, that is 1. That is air or free space, relative permittivity is not 1. See, K's value is 1. This K, this will be 1. So see, 1 by 4 pi epsilon, this will be q1 q2 by r square. Now see, I have this value epsilon, and if I wish to represent or relate it through epsilon naught only, means for the vacuum or air, so I can use any of these two relations. So let's use this one. This is easier because we know the value of K, we know the value of epsilon naught, so we'll be able to calculate it. So if you substitute this equation, this value of epsilon in this equation, you will get 1 by 4 pi. Instead of epsilon you will have K epsilon naught q1 q2 divided by r square. So what is 1 by 4 pi epsilon naught q1 q2 by r square? If you remember, q1 q2 K q1 q2 by r square, in air it was 1 by 4 pi epsilon naught q1 q2 by r square. This was for air, right?
Yes, ma'am.
Now see, if you just leave this K over here, rest of the terms are similar to what was written over here, means for air1. So if you see, for any medium that you are calculating, this is for a medium we are calculating, this will be F air, whole term is for F air divided by the constant, and this constant is known as the dielectric constant. So K is usually greater than or equal to 1. This value of this K, this is usually greater than or equal to 1. Equal to 1 for free space only. For water, K is equal to 1 for water, and we know the value for air, 9 into 10 to the power 9. So it's usually greater than 1. So that's why, since this is greater than 1, obviously if air will be greater than F medium. So force in any medium will always be less than or it will be equal to the force in air. So this is what is meant, what is the concept of dielectric constant, and this is the concept of permittivity. So if you wish to relate permittivity, relative permittivity and dielectric constant, you have this relation with you. This is dielectric constant, this is permittivity of air, and this is absolute permittivity for any medium. When you compare it, when you take the ratio, you get the relative permittivity or you can get the dielectric constant. Any doubts or any part that you wish to repeat? Just let me know. So if rest of the terms are clear, just note this down. Otherwise, wherever you get stuck, you can ask me right now. Then we'll begin with a new topic.
Could you scroll down? Thank you.
So all of you have done till now?
Yes.
All right, okay, let's move to the next topic. Electric field. So let's see the concept of electric field, what is meant by electric field. Now see, just to understand electric field, we should know, like if I say I have a positive charge. All right. See what will happen if I bring another positive charge. Let's say if I bring another positive charge, this small plus q. So what will happen if I bring this small plus q charge towards capital plus q in the proximity of this? What will happen? Will there be any change or it won't affect?
Can you repeat?
If I have this plus q, positive plus q charge with me, and I bring this small q, this charge in the vicinity of this capital Q, so will we be able to see anything, or it won't affect? There will be repulsion. Yes,
There will be
right.
some electron repulsion.
Electronic repulsion. Yes, right. There will be repulsion. Why it will repel each other? Because both the charges are positive. It is plus q and
Like
it is
charge
also
repels.
the like charges repel each other. So see, what happens if I keep this charge over this distance? Then I am observing that nothing is happening. But whenever I bringing this plus small q charge in the vicinity of this capital Q, nearer to it, I am experiencing some electrical environment. Whereas when the charge was far away, was kept far away, there wasn't any experience of electrical environment.
And force is inversely proportional to r square.
Distance, exactly. So as I'll keep on increasing the distance, electrical activity will get reduced. So that's why I wasn't able to experience this electrostatic repulsion when this charge Q was kept far apart. Now this charge Q is near this charge capital Q. So this is observed that this charge plus Q, this charge plus Q, this has a certain electrical environment. So if this electrostatic force acts between two charged bodies even without any direct contact between them, so the nature of this action distance force can be understood by this concept of what we have known as electric field. So if you consider a charged body carrying a positive charge Q, which is placed like this is the setup, then it is assumed that the charge small q, this charge capital Q, this produces an electrical environment in the surrounding space, which is known as the electric field. So an electric field is said to exist at a point if a force of electrical origin is exerted on a stationary charged place at that point. So this line means simply this plus q is the stationary charge. Now it has certain electrical properties around it. It has certain electrical environment around it. So whenever you bring a test charge near it, it will experience certain force. Had it been a negative charge, it would have attracted it. Now here in this case, it is a positive charge, so it is repelling it. So the space around the charge in which electrical properties can be experienced, that region or that space, that field is known as the electrical field.
Ma'am, could you explain this again?
All right, see, there is this positive charge plus q. All right, now see, this charge plus q is having its certain electrical properties. It will be executing repulsion forces or attraction forces. So whenever you bring a negative charge towards this positive q charge, it will attract each other. And if you bring up positive charge towards this plus q, it will repel each other. So what happens? Whenever this plus q, this solitary charge is kept, this is a stationary charge, this is placed, it is having certain environment around itself in which electrical properties do exist. There's a space around this positive charge where electrical properties or all the electrical environment can be felt. If you bring any charge, let's say I bring this positive q charge in the vicinity of this, in the area, in the space of this circle that I have drawn, the boundary that I have drawn where the electrical properties can exist. This boundary just represent this circle that I am drawing, these dotted lines of circle, these just represent that only in this area electrical activities can be felt. As you move away from this point, this region, electrical activities get reduced because, as you rightly said, because of inversely square proportional rule. So this space around any charge where you are able to feel any electrical force or any electrical properties are able to exist, that region is said to be electric field, that field around any charge where these electrical phenomena can be felt. So if you bring a positive charge in this field plus q, it will experience a force of repulsion. But if you bring this charge further away from it, like let's say this is the distance, this is position 1, this is position 2, So in this case, in position 1, what is happening? Charge plus q and the small charge plus q. Both of these charges are very far from each other. So it is also having its certain electrical property, this charge small q, and this is also having its certain electrical field plus q. But since both of these are so far away from each other that both of these are not able to experience any electrical force because of the inversely square rule. If you bring this small plus q charge closer to this capital Q over here in this region of this, so what will happen? Both of them will repel. So this certain confined field where electrical origin is exerted, or any stationary charge, or you can simply say any space around a charge where electrical properties can be felt or electrical environment can be experienced, that certain space or that field around any stationary charge or a single charge, that is known as the electric field. See, in the concept of electric force, in forces we need two charges. Forces come by interaction. So when we had two charges kept together, both of these exerted force on each other. So two charges were required. A single charge won't be able to exert force. What the thing or what the property a single charge can exert is the concept of electric field. Any charge will be having certain field around itself where electrical phenomena can be experienced. So see, this is electrical field is the space around charge. This is the region, this confined region in which its electrical properties can be experienced. Okay, just tell me one thing. According to you, is this a contact force or a non-contact force? Electrical field. Is it a contact or not? Non-contact force. Non-contact, because if you are even keeping this charge plus q here, this will be also having its certain field. This is also having its certain field. So both of these will be exerting force on each other, whatever is the distance, what we have studied in Coulomb's law. So this will be, yes, non-contact, right? So this will be a non-contact force. Both the charges have their own fields, that's why it is a non-contact force, and you don't need to place them together. Like in case of in laws of motion, you must have studied normal reaction. It only came when two bodies were kept in contact with each other, then only a perpendicular force that applied on the surface, that was normal reaction. So that was a contact force which occurred. It couldn't be experienced if both the objects were kept far apart, but electric field can be felt if the charges are kept far. So to explain non-contact force, non-contact forces, we require this concept of electric field. We require the concept of field. This concept of electrical field, this is required. Now see, how can we explain non-contact force regarding this? See, if I say this is a source charge plus q, this is a source charge with me. Let's say this is a source charge, means a stationary charge which is executing its electrical field. So it is executing its electrical field, let's say in some direction. Now I bring a positive unit charge in the vicinity of this, near this. So what will happen? I have this plus q with me. This is the electrical field of this. Let's say this is the electric field of this plus q. It is exhibiting its electrical field lines. So electrical field is there. So whenever I'll bring this positive charge, So what will happen? Whenever this positive charge is kept, it will execute properties of repulsion or attraction that we have discussed. So that's how it will explain that it is a non-contact force. Had it been a contact force, then we were required to keep both these charges together. Since these are non-contact force, this repulsion or this forces of attraction can be easily felt from a little distance. So that's why we say to explain the non-contact forces or electrical forces are non-contact forces. So just to explain this phenomena, we require concept of electric field also. One more thing, one difference that comes from electric force which we have studied is that this electrical field, this is a concept of a single charge. It is a property of one charge. Since it's a property of one charge, this line simply means that it's a property of one charge. Means if you have a solo charge kept, it will also have its electrical field. But when you are required to calculate force, you won't, if I provide you with a single charge Q, you won't be able to calculate the force. You require another charge and the separation between those charges. So that's why that makes Coulomb's law valid for two or more charges. For electrical field, minimum charge requirement is what? Single charge. Also, one more thing, that this electric field, this travels with speed of light. What is the speed of light?
3 into 10 raised to 8 meter per second.
Correct. 3 into 10 to the power 8 meter per second. So the electric field lines, these also travel with the same speed. All right. So before we move on to this topic, electrical field intensity, just write down these points of electrical field. Then we'll go into detail of these. And wherever you are having doubts, you can write me. Yes, done.
Yes.
All right, so electric field is said to exist at a point if force of electrical origin is exerted on a stationary charged body placed at that point. Now see, if we were to know what is meant by electric field strength or intensity, so electric field strength, electric field density, not electric field density, this actually means electric flux density. This is electric flux density. So she will see what is this. Electric field strength. So again repeating, the whole concept will get revised. Plus Q is the source charge. Let's say this is the source charge. This is the source charge that we have. Now see, I bring a unit positive charge over this side. I bring a unit positive charge in the vicinity of this. So see what will happen. I call this charge as a test charge. This is a test charge. Test charge just in order to see whether this plus Q charge is a positive charge or is a negative charge. So if small plus Q is a test charge, this will just help us to know if it is a positive charge or a negative charge. If it is a negative charge, then simply both of them will be attracted towards each other. If plus Q had it been a negative charge, then this would have been the case. Now, since plus Q is a positive charge, this test charge has its positive value. So we say that both of these will repel each other. So in order to check that, we need a test charge just to see both of these are repelling each other or what is happening. So what will happen? This will get repelled by some force, let's say Fe. F is that only. F is if both of these are separated by a distance small r, then F will be equal to K capital Q small q divided by r square, the way you have calculated Coulomb's law. Now see, all the electrical force experienced by the test charge, all the electrical force experienced by this test charge due to field of this source charge, that is known as the electrical field intensity. Whatever electrical force this is experiencing because of the electrical field that is present or that is exerted by the source charge, that is known as the electrical field intensity. All right. So whatever forces are occurring, let me write down it. Electric force Fe. This is experienced electrical force experienced by test charge. What is the test charge? Plus Q or small q?
Small q.
Small q. So this charge small q due to field of what?
Source charge.
Source charge. Due to field of source charge. This is due to field of source charge positive capital Q. This is what is meant by electrical field strength or electric field intensity. So see, just to represent this mathematically, what we have understood, we can write this electrical field is force experienced. This is the same force which we have studied in Coulomb's law. So electric force experienced by this test charge. And we can write this limit Q tends to equal to 0. Now see what is meant by limit Q tends to equal to 0. When we write like this, limit anything Q or any quantity that tends to equals to 0, this shows that force experienced by this charge small q, this is negligible. And this shows if the force experienced by small q is negligible, this shows that capital Q is the stationary charge and hence cannot move. So this shows that hence capital Q cannot move. Value of Q is not equal to 0. See, this represents that the force experienced by Q is 0. Limit Q tends to 0 is representing the force experienced by Q is almost negligible. That is so small that we can say the source charge is stationary. All right. Q is not 0. Q has its value. Now see, electric field is now force. Electrical field can be given by force per unit charge. From here you can say whatever, or you can even equate and write is that force per unit charge. But see, force experienced by charge Q will be negligible and hence charge Q will not be able to move. So whatever forces this test charge or the small Q is experiencing because of the field of the source charge, we called it as electric field strength or intensity. Now, electric field is also a vector quantity. Electric field is a vector quantity. So can we directly add electric field together algebraically?
No, ma'am.
Vector quantities cannot be added directly using algebra. We need vector laws or proper laws. So we will be studying superposition principle that will help us to calculate various electric fields which are present. Now see, regarding the direction, vector quantities have direction as well as magnitude. So regarding the direction of this vector quantity, it is same as the force experienced by the test charge. Force experienced by test charge. So if I say this was a positive charge and the direction of electric force is towards my right. So what is the direction of electric field? Direction of electric field is same as that of force experienced by test charge. So if force is moving or the direction of force is right, so exactly the electrical field will also be towards the right. So this will be the direction of electric field, similar to the direction of electric force. For a negative charge, if I say had it been a negative charge, electrical force direction was towards the left side. So electrical field will also be towards the left side. So whatever will be the charge, the direction of electrical force will be accordingly, and the direction of electric field will be according to the electrical force. Electrical force is same, the Coulomb's law which you have studied. Now see, regarding SI unit, if I say electric field is charge force per unit charge, as we have seen, electric forces per force per unit charge or force experienced by the test charge. So write me in the chat box right now. You know the SI unit of force, you know the SI unit of charge. What should be the SI unit of this electric field? Yes, right. Correct. It will be Newton is for force and Coulomb is for charge. So SI unit will directly be Newton per Coulomb. And we have one more unit that would be clear over this chapter. We have volt per meter as well. So when we'll discuss potential, when we'll move on to the next chapter, there you will understand how this SI unit has been derived. For till this chapter, you can remember Newton per Coulomb. Newton is for the SI unit of force and Coulomb is the SI unit of charge. So see, if I say this test charge, what I'm having, this Q, this is a unit charge. Unit charge means it is having the magnitude 1. So what will be the value of electric field?
Electric force, value of the electric force.
Electric field will be equal to electric force value. See, if I say electric field is F by Q and the magnitude of this is +1 coulomb. So simply we can say electric field will be equal to electric force. So now you can easily get the definition of what is electric field. Electric field at a point. This can also be defined as force experienced. See, electric field will be equal to the force experienced. Experienced by what? When was this electric field equal to this electric force?
When Q is equal to 1.
When Q is equal to 1. So when we say this is force experienced by unit positive test charge. This is the value of electric field. This is the definition. This can be another definition of electric field. So electric field is equal to the force, electric force, which was experienced by any unit positive test charge, which is brought near the source charge. Let's do a question based on this. See, if I say a test charge, the magnitude of this test charge is 10 to the power minus 3 coulomb. This experiences a force of 10 to the power 2 Newton due to field of a source charge. Because of a source charge, a test charge is experiencing a force that is 100 Newton, and the magnitude of the test charge is given as 10 to the power 3 minus coulomb. Now you have to calculate the magnitude of electric field because of this charge. So just do one thing. First, note down all these points, and when you are done, then write down the question. Just copy it down. Yes, Shavya, your answer is correct. So yes, written till here.
Yes, teacher.
All right, see. So it says test charge of 10 to the power minus 3 Coulomb means the value of small q we have as minus 10 to the power minus 3 Coulomb. This experiences a force of 10 to the power 2 newtons. We have to calculate the electric field. So electric field is given by force divided by the test charge that we have. So this will be simply 10 to the power 2 divided by 10 to the power minus 3. This will be 10 to the power 2 into 10 to the power 3, that becomes 10 to the power 5, and the unit will be Newton per Coulomb. Is this clear?
Yes, ma'am.
Now see, electric field for a point charge. See, this is very easy. If you have a positive charge, this is small q test charge. Let's say capital Q is the source charge. So this is the source charge that we have, and this is the test charge that we have. So what is the force experienced by both of these charges if the separation between them is small r? What is the value of electric field force? Electric force will be
K Q1 Q2 by R square.
what is Q1, what is Q2? We don't have Q1, Q2 right here.
Small q and capital Q.
Yes. So K Q by R square. Yes. So this will be K capital Q small q divided by R square. So this is electric field, and now this is electric force, not electric field. This is electric force. According to Coulomb's law, we have this as electric force with us. So this is Coulomb's force. Now see, according to Coulomb's law, we have this electric force. So a value of electric field is force divided by the test charge that we have. So this simply means value of electric force is K capital Q small q divided by R square by small q. This is value of electric force K capital Q small q by R square, and this is the test charge that we have. So what will happen? Test charge value will get cancelled. Electric field will be equal to K capital Q by R square, which you can write it as 1 by 4 pi epsilon naught Q divided by R square. So in case of electric field, we don't have the test charge with us. So this is only equal to 1 by 4 pi epsilon naught Q divided by R square. And this formula, this is valid only for point charges. Only for point charges. It's just that test charge gets vanished. Now see again, direction for positive charge. Regarding the directions. See, for positive charge, electric field will be away from the charge. Why it will be away from the charge? Because if a positive test charge is kept, then it will move away. Similarly, if you keep a negative charge, then this will move towards the charge. This will move towards the charge. So if you have positive charge, electric field will be in this direction for this charge, and you have a negative charge, then the direction of electric field be towards this charge. So like if I give you example, and let's take this random point. Let's say I have taken plus 2 Coulomb charge. Tell me, will the direction of electric field for this point I have taken, this point A, will it be towards the left, right, up, down, where? Yes, right, left, up, down. Where will be the direction of electric field for this positive charge? If this is a positive charge, then right. It will be towards the right. What about others? It will be towards the right only. See, away from the charge. Away from the charge will be this direction only. If I take this point B, away from the charge will be on the left direction. If I take a point C, away from this charge will be upwards. If I
Upwards.
take a point D,
Downwards.
this will be downwards. This will be downwards. You just have to see away from the charge. Let's reverse the magnitude of this charge. Let's say this is minus 2 coulomb. So if you take the same point A, this will be towards this charge.
Towards
now towards the charge. So in for B, will it be right or left?
Right.
It will be in the right hand side. C, for the point charge C, now it won't be away from the
Downwards.
charge, downwards. And reverse, it will be for D, it will be towards the charge. So whatever charge you have, you just have to take the direction according to the value of the source charge. If the source charge is positive, then you have to take the direction of electric field away from the charge. If you have negative source charge, then you have to take the direction of electric field towards the charge that you have. Now see, we had discussed in the beginning of this class only regarding dielectric or electric constant and relative permittivity. So this 1 by 4 pi epsilon naught q divided by r square is valid for point charges, and this is valid for point charges placed in air only. So if we change the medium, and we have a different medium, so as we have studied, this won't be now epsilon naught only. It will be having one more quantity with it. That was 1 by 4 pi k epsilon naught q by r square, right? This will be k epsilon naught for a different medium. Or you can also write it as E is equal to k, not k. This will be equal to E 1 by 4 pi epsilon q by r square, whatever you have studied for Coulomb's law. That is just valid. It's just that this is valid for a unit positive test charge. In Coulomb's law, you had both the charges which were experiencing the field. All right, so just note these down for electric field for a point charge. If anybody wants the solution of it, just let me know. Otherwise, just copy it from here. See, this says a point charge of 10 Coulomb at origin is kept. If I say this is the origin, so 10 Coulomb charge is kept at the origin. You have to calculate electric field at a point A 2, 0, 0. What is meant by this? Which axis is this 2 on?
X-axis.
X-axis. Yes, you have to use this relation only. So this will be 10 Coulomb. This is kept on x-axis. So x-axis at a separation of 2 meters, or make it 3 meters only. That will ease your calculation. Make this 2 meter as 3 meter only. This will make the calculation easier. So if this is the x-axis, let's say this is the x-axis. So at a point A, which is 3 meters from the origin, you have to calculate the electric field. So electric field, for calculation of electric field, see, electric field is equal to K capital Q divided by R square. 10, yes, 10 to the power, correct. So see, K, what is the value of K?
9 into 10 to the power 9.
9 into 10 to the power 9. And Josefa, what is the value of capital Q? Yes, Josefa? Yes, positive plus 10. Okay, Memuna, what is the value of small r that we have?
Three meter.
Right. So we have all the values with us. K is 9 into 10 to the power 9. Capital Q is 10 coulombs, and R square. R square is mainly 3 square. So this is 9 into 10 to the power 9 into 10. 3 square is also 9. So 9 gets cancelled. 9 into 10 to the power 9 into 10. This becomes 10 to the power 10 Newton per coulomb. But see, the question has specified as magnitude and direction. So if this is a positive charge, what will be the direction of electric field?
Wait.
Yes, Shravya, could you repeat, please?
Away from the charge.
Away from the charge. So which axis, which direction? Away from the charge represents which axis?
Negative x-axis.
Negative x-axis will lie on this side, no? Beyond the origin. You have to calculate electric field at this point. Away from the charge at this point. See, this is your O point where the charge is kept. You have to find out electric field. The way I was giving you the previous example, while keeping plus 2 coulomb. Here, instead of plus 2 coulomb, you have plus 10 coulomb. So if point you have to calculate, let's say point A is the charge, is the point where you have to calculate the electric field. It will be on the left or right.
Right.
Right. Anybody else? Atif?
Will be towards the right.
It will be towards the right. See, away from the charge will lead us to this direction. So which axis is this? Y-axis, Z-axis, X-axis?
Along the positive x-axis.
Positive x-axis. So unit vectors. Do you remember your unit vectors? I cap, J cap, K cap. So which one will this be?
I cap.
I cap. It will be positive I cap. So this will be 10 to the power 10 I cap Newton per coulomb, which represents the direction of electric field is towards the positive x-axis. Is this clear?
Yes, teacher.
All right. So just note down this question as well. Then we'll stop here.
Done, teacher.
All right, all of you have done? Or is there anybody still writing? Just write done in the chat box and I'll know that all of you have done. Huzaifa, are you done? Yes, yes, you can leave. I think if that time will be there, you can leave. All those who
Thank
have to write,